Happy Tuesday afternoon. Finishing up derivatives.
I'm just talking about this one.
Implicit. Right, so this is the technique that we use if y is implicitly defined as a function of x. What we do is we just differentiate both sides of the given relation and then algebraically solve for dy dx. And this is the method that I use to derive the inverse trigonometric derivatives. So remember, there are 6 of them. The derivative of the inverse sine function, 1 over the square root of 1 minus x squared. Derivative of inverse cosine, negative 1 over the square root of 1 minus x squared. Derivative of inverse tangent, 1 over 1 plus x squared. Derivative of inverse cotangent is negative 1 over 1 plus x squared. Derivative of inverse secant, 1 over the absolute value of x times the square root of x squared minus 1. Finally, the derivative of inverse cosecant, negative 1 over the absolute value of x, square root of x squared minus 1. Bless you. Notice the relationship between the inverse trig function and its co-function. be important later. And our final technique, logarithmic differentiation. There is still another type of function we haven't looked at yet. Function raised to a function. Simplest x to the x. None of the rules we have can handle that. So we have to use this technique. We're given a function y equals f of x. What we do is we take the logarithm of both sides and then differentiate it using implicit differentiation. Specifically, we use the natural logarithm. Right, so what we're doing is we're finding the derivative of dy dx for natural log of y equals natural log of f of x. Logarithmic differentiation can also be used if you're given a really difficult quotient. You could then use logarithmic to simplify it, simplify the process. We're going to find dy dx for this curve. This is what we do. Left-hand side, what kind of function are we dealing with? Sum of functions. So go term by term. Derivative of x to the fourth.
4x to the third.
Derivative of y squared.
2y dy dx.
Right, that is general power rule. And then derivative of y. What's the derivative of 7?
0.
0.
I thought we were doing the derivative of y.
Derivative of what?
I thought we were doing the derivative of y.
Yeah, we did. It's dy dx. Now we algebraically solve for dy dx. When you're trying to solve for an unknown, you need to do what?
Do all of the unknowns on one side, and then the rest on the other side.
You need to isolate it. Now what?
And then divide out the 2y.
If you do that, you're going to have a 1 over 2y dy dx. Right here.
You can factor out 2y dx.
First, factor out that dy dx. And then divide by 2y plus 1. There's dy dx. Remember, y is an implicit function of x. Right. Now, I'm obviously not going to write this part out every single time. The whole ddx of both sides. I'm just going to skip right to that. Find the derivative of the left-hand side.
So this times x to negative 3 and 3. Same with y, except it's multiplied by the right x.
What about the right-hand side? Which was 0. Subtract 2/5 x to the negative 3/5. Divide by 2/5 y to the negative 3/5. Oh, I forgot negative. Drop my negative. So write it that way. And however you write it, doesn't matter. There's our derivative. There's dy dx. So not really that bad. Just going to require more algebra. Oh, by the way, this process is a lot easier once you learn to calculate. You actually don't have to do any of this. It's just a one-step process. But you'll learn that in a year. D dx for the left-hand side. What is it?
Negative sin x plus y cos y cos dy dx
Cos of what?
with y.
And the right-hand side. Oh, this one's easy too. Add sine of x. Divide by cosine of y. Can that be simplified? Nope. D dx, left-hand side. So d dx of the left-hand side.
All right, 2x plus e squared plus 2y times the natural log of 2, and all of that last term there times dy dx.
So it's 2x plus e squared plus what?
Plus 2y
2y.
times the natural log of 2, then all that last term times dy dx.
Like that?
Yes.
I agree, except for all of it.
Was it the x squared and the squared be a product rule? So it'd be x squared times e squared plus 2x times e squared plus 2 to the y ln 2 dy dx.
I agree, except with one term. I won't tell you what term. And I won't tell you what about the term I disagree with.
Probably the last one, that's the only one that stayed consistent both times. Only one pretty wrong there.
Or was it a x squared e squared, the term on the right or not? The x squared e squared term on the right.
What about it?
It's a product rule, so you gotta multiply it.
That's what that is.
Is it missing a 2 times the x squared b squared?
So that I agree the issues with that term.
Shouldn't be there,
Why?
because the product rule comes out to be 2x e squared.
Product rule does? No, I mean,
Right.
technically yes, but you don't need product rule for that.
Oh, because e to the squared is just like.
E squared's a number. That's a constant multiple rule. You can use product rule, but the derivative of e squared is 0. Where?
Just got rid of it.
Yeah, it doesn't belong there.
Alright.
E squared's a constant. Treat it as constant multiple.
Let's see that.
What do we have to do? Again, that's the only calculus that we actually do throughout this entire process. So what should we do first? Like a second. It's already took the derivative.
Subtract 2x times e squared on both sides.
Now what?
Divided by 2 to the y on 2.
We can expand that 2 to the 4.
Hmm?
Can we expand that 2 to the 4?
How would that simplify? There's actually two ways to simplify it.
2 to the 1 minus 1.
Okay, there are three ways to simplify it. There's negative 2 to the what?
1 minus 1.
Like that?
Does that work?
Well, that's what I'm asking you. Is that what you got?
Yes.
That's one way. Which is not the way I would do it,
But it's suggested.
but it works. There's one way, or a second way. Keep the 2 in the denominator. Just because the y is positive. But there's another way. So this is probably the way that I would write it. Now, yeah, I haven't even talked about higher order implicit differentiation.
I'd like to talk about it.
I don't want to do it.
You don't do it.
Doesn't mean I won't make you do it, but I'm not doing it. It sucks. Could also write it that way.
How?
2 to the minus 1 is 1/2, isn't it? So it'd be log of 2 to the 1/2 power, which is log of root 2. The exponent law of logs. How do I write 2 to the y minus 1? Then I just bring the 2 down to down there is 2 to the minus 1, which is 1/2, isn't it? 2 to the minus 1, 1/2, same thing.
Oh, yeah.
Well, then isn't that 1/2 times log of 2?
Okay.
And then from there, just simplify it. DDX, left-hand side.
squared of y times dy dx.
That?
Yes.
You misapplied the rule.
2x times tan y plus x squared times secant squared y times dy dx.
That's it. Equals. Like so. Subtract the 2x tangent of y. Divide x squared secant squared. Like that. Can that be simplified? No?
No.
Can. Is it required? No. I can write this as a single trig function, or in terms of a single trig function. The question is how. What's secant?
One over cosine squared.
Secant's 1 over cosine squared.
Cosine.
Secant's 1 over cosine, so 1 over secant squared is cosine squared. What's tangent?
One sine over cosine.
Multiply that by cosine squared, what are you left with?
That's cosine.
You're missing a term. Sine times cosine. But I said I can write that as a single trig function.
Sine 2y. Edit sine 2y.
Make the sine of 2y over x. Two sine y cosine y is the double angle identity for sine. So to me, that's much simpler. than the original. It's subjective, unless you consider that this is a dictatorship. Then it's objective.
Completely arbitrary.
It's not arbitrary. In a dictatorship, whatever the dictator says goes. So it'd be objective at that point.
In this hypothetical, who's the dictator?
Who do you think would be the dictator?
This is arbitrary.
It's my answer.
Everything is arbitrary. Just because something's defended doesn't make it arbitrary. Yeah.
This was actually not terrible. DDX, left-hand side.
For parentheses, the function inside of there.
I don't see a function.
Expression.
So what is it?
3x squared plus 2 second. Parentheses, 3.
What do you think this is? Calc 3, where we're dealing with multivariate functions?
Times 6 x plus 4y dy dx equals 0.
Just like that?
I think it's right.
Anyone else? No?
There is a major issue.
We need parentheses. Okay, I did that. For the record. I'm the only one who speaks, sorry. Not hard. Only parentheses.
You're the only one who speaks.
Where the promises and measures.
You're disregarding, you're disregarding something else. So, I'm sorry.
That's okay, I'll just remember that when I start grading a test.
When you start
Were the parentheses the major issue?
Yes.
Okay, so that's what it was.
Because without the parentheses, that is completely different. That is right, completely different. What would you do now?
So, take that, wait, no. No, we can't do that. Multiply them.
You want to expand that out? You can.
I wanted to subtract the thing, but we can't do that. You know, like the other term.
So what do you think we should do? I mean, you can expand it out if you want to.
Try simplifying it.
How?
I wasn't sure, that's why I jumped right to it.
Can we just multiply it out, make it look really ugly, and then isolate it, and then?
You can.
Okay.
Can we just divide by 4 times 3x squared plus 2y squared to the third?
I definitely agree with the dividing by 4. Why would you be able to divide by the 3x squared plus 2y squared all cubed? True, but there is a value you're not allowed to divide by. You would be allowed to divide by 0. What if that 3x squared plus 2y squared is 0? You wouldn't be able to divide by it, would you? So why can you divide by it?
We can't. Even if we multiply by the 4 and cube it, that wouldn't make it not zero, right?
You can, I'm asking why.
We're assuming the term on the right is 0.
Almost certainly is 0. I can divide by 4 because it's not 0. So why am I also dividing out by that 3x squared plus 2y squared cubed? By doing so, I'm saying it's not 0, right? I'm saying that'll never be 0, so I'm safe to divide by it. Why is it never 0? There are 2 reasons you could give. Actually, one reason. When is the only time that is 0?
And then x and y are both equal to 0.
Can x and y both be 0? So let x and y both be 0. Look at the original relation. What do you get? That would give you 0 equals 2, which is bologna sausage. Specifically, I can divide by it because for every xy value, 3x squared plus 2y squared is the 4th root of 2, which is most certainly not 0. Which makes this problem a hell of a lot easier. Because if it could be 0, then I wouldn't be able to do that. Now it's just simple. It's a simple linear equation now. Subtract 6x. Divide by 4y. And what's wrong with that? How's it simplify? And you're left with what?
3x over 2y.
And there's dy dx. d dx, left-hand side.
Two x plus dy dx plus 2y plus x over x squared plus xy plus y squared.
That.
In the middle, it's from X and Y. Anyone else would like to-
So what is that middle?
Y plus X.
I agree there's a y plus something.
Y plus x dy dx.
And what does that equal?
0.
Do we have an issue? What would cause an issue? If what's 0? Can the denominator be 0? No. Because the domain of log does not include 0. So no issue. What do we do?
Multiply both sides by the
We just get rid of the denominator.
What did we just do down here?
You can just get rid of it.
All right.
When is a fraction equal to 0?
When the top could be.
When the numerator is 0.
Yeah.
Or multiply both sides by that denominator.
Doesn't matter.
It doesn't in this case because we're saying it equals 0. Now what?
So, start subtracting some stuff.
What do you want to subtract?
Start with 2x from both sides. Yeah, just subtract 2x from both sides, do that over.
I'm going to do 2 steps at once. I'm not going to just subtract 2x. I'll subtract 2x plus y.
Right?
And I'll write it that way so I have as few negatives as possible. Now what? Now what?
Now divide both sides by x plus 2y.
Can that be simplified? I can't. Oh wait, yeah, it should be x plus 2y. There is one thing you could do. It's not really simplified. And that's just write it symmetrically. Which again is something I would do because I'm a fan of symmetry. Which makes decorating very fun. Because if it's not symmetrical, I tear everything down and start all over. dy dx, left-hand side.
Alright, so all these first part parentheses. So in parentheses, 2x squared plus 2y squared plus 2x. Those parentheses. The fact that you're not writing this here.
Yeah, well. 2x squared plus 2y squared plus 2x.
Would you rather me leave the 2 out?
Oh, I see what you're doing.
Yeah, I can leave the 2 on the outside.
I see what you're doing. Yeah, let's just leave it on the outside.
Alright, well in that case, 2 on the outside, open parentheses, x squared plus y squared plus x. And another open parentheses, 2x plus 2y times 2y dx.
I'm going to write y prime for my sanity for this problem.
Okay.
That same thing.
Plus 1.
Right hand side.
Two x plus 2y dy dx.
And now I want you to keep in mind, as we finish this problem, that was the calculus. What do you want to do next? Hmm?
I think
Take out the 2 from where? That's the first thing I would do. Get rid of those 2's. Because you have a common 2 on both sides. Which is why I didn't put the 2 through. Now what do you want to do?
Hear me out. I think we should just expand it and then try to cancel some stuff out.
So expand that out.
Yeah.
It's a viable option. Expand it out, what do you get?
I'll get back to you.
We'll say it's not what I did. But this might actually be better than what I did.
Keep going.
Did you divide by 2x plus 2y?
No. I divided by the first term. But then that gives me fractions and then complex fractions that I have to simplify out anyway. This method may actually be better. And there are no common terms, I don't believe. Oh, there is. There are some common terms. Nice. I think there's only one, though. There's the x squared and the 2x squared. I think that's it, though.
Oh, yeah.
I don't see any other common terms. So, instructor's prerogative.
It's so much easier.
Oh, well, that's also nice. There's an x on both sides. We're just going to wind up dropping out. So let's subtract y prime from both sides. And subtract a nasty term from both sides as well. So I'm going to move all my y primes to one side and everything else to the other. There's one side. And everything that I'm going to be subtracting is positive. And the x's wind up dropping out. And again, just for my sanity, just going to bring that to the next slide. In fact, got a y prime now, right? And now, I'll switch to the Leibniz notation.
Wait, that step at the top, is that after the x was factored out?
That's just repeating it from the last slide.
Or was it factored out on the last slide?
No.
Alright, so still writing this way.
So it's the same thing as the last step.
Right, thank you.
And now divide. There's dy dx. I'm going to be honest, I liked that a lot better than what I did. I divided both terms by that x squared plus y squared plus x, and wrote the right hand side as two separate fractions, which means I had to find a common denominator, and then I had compound fraction, and it was, generally speaking, not fun.
Yeah, I don't think there's any way to make this one fun.
That's what I said. That's why I wanted you to keep in mind that the first thing we did was the only calculus. Everything else was algebra. We'll pick up right there on Thursday.